Hello, in today's video, we will solve the exercise 25 and 26 from the chapter 2 of book Contemporary Abstract Algebra 10th edition by Joseph A. Gallian. Question number 25 is actually the law of exponents for a billion group, and the statement is let A and B be elements of an abelian group and let n be any integer, then show that AB whole to raised power n is equal to A to raised power n, B to raised power n. And also it is asked that is this also true for non-abelian groups? So let's start the solution. We will prove the result by using the mathematical induction. Okay, let n is equal to 0, then AB to raised power n is identity element, and similarly A to raised power 0, B to raised power 0 is also identity. So this means AB to raised power 0 is equal to A0 B0. Also, if we take n greater than 0, say n is equal to 1, then AB to raised power 1, which is actually equal to AB, and that is A1 B1. So it is true for n is equal to 0 and n is equal to 1. Let us suppose that our result is true for n is equal to r. R is an integer. Then AB to raise power r is equal to AR PR. This is our assumption. Okay. We will prove for n is equal to r plus 1. Now consider AB to raise power r plus 1, and that can be written as A B to raise power r into AB. We can say to raise power 1 or simply AB to raise power r AB. And from our assumption, we know that AB to raise power r is equal to AR PR into AB. Okay. And since the group is abelian, so we can write it as AR into R, BR into B, and that is AR plus 1, BR plus 1. So this is, it is true for all positive integer, and also it is true for 0. So n is greater than or equal to 0, it is true. Now we have to prove for negative integers. Let n is less than 0. We say n is equal to minus k, where k is positive integer. So we consider AB to raise power n, which is equal to AB to raise power minus k. And If we if we see, this can be written as AB raised power k minus 1, and that will be AK BK minus 1, because now k is positive integer and AB raised power k is already equal to AK BK from our this result, and that can be written as A raised power minus k and B raised power minus k, because group is abelian. Because in when we take the inverse, the order is reversed, but because group is abelian, so we can take the same order. And in this way, because minus k is equal to n, so it is a n b n. This means a b raised power n is equal to a n b n is true for any integer n in abelian group. And the second part was, is it true for non-abelian group? So answer is not true for non-abelian group, because in non-abelian group AB is not equal to BA. So in this way, if we take AB to raise power 2, we will get AB, and that is not equal to A square B square in general. So it is not true in non-appealing group. The next question is 26, which is socks shoes property, and the statement is, draw an analogy between the statements A B whole inverse is equal to B inverse A inverse and the act of putting and taking off your socks and shoes. Find distinct non-identity elements AB from a non-abelian group such that AB whole inverse is equal to A inverse B inverse. Find the example that shows that in a group it is possible to have AB raised power minus 2 is not equal to B raised power minus 2 A raised power minus 2. What would be an appropriate name for the group property ABC whole inverse is equal to C inverse, B inverse and A inverse? Let's start the proof. Okay. Putting your socks and then putting your shoes, and the inverse of this statement is taking off your shoes and then taking off your socks, because it is not possible to take off your socks before taking off your shoes. So now we consider a group quaternion 4, which is group 1 plus minus 1 plus minus iota plus minus j plus minus k, with the property that I square is equal to j square is equal to k square is equal to minus 1, and ij is equal to k, but ji I is equal to minus k. And similarly, jk is equal to I, but kj is equal to minus I, and ki is equal to j, and ik is equal to minus j. Now we take a is equal to minus 1 and b is equal to iota from this quaternion 4 group. Now we consider AB whole inverse, which is equal to minus 1 into iota inverse is equal to minus iota inverse. And we know that the inverse of minus iota is iota, because when we multiply iota with minus iota, we get 1. Okay. And that can be written as, okay, we consider A inverse, B inverse. Minus 1 inverse and iota inverse. We know that the inverse of minus 1 is again minus 1, because when we multiply minus 1 with minus 1, we get 1. This quaternion 4 group is group under multiplication. Okay. And the inverse of iota is minus iota. And when we multiply minus 1 with minus iota, we get iota. So this shows that AB whole inverse is equal to A inverse B inverse. That was first thing which we want to show. Now consider A is equal to iota and B is equal to J from this quaternion group 4. Then consider AB to raise power minus 2 as ij to raise power minus 2, which can be written as ij square to raise power minus 2. And we know that ij is equal to k and k square. So instead of this ij, we have written k square. And we know that the k square is minus 1, and minus 1 to raise power minus 1 is equal to 1 over minus 1, which is equal to minus 1. And now we consider b minus 2 a to raise power minus 2, we get, because b is j, so j to raise power minus 2, and similarly a is I, so I to raise power minus 2, and that can be written as j square minus 1, I square minus 1, and that is j square is minus 1 and I square is minus 1. So instead of j square, we have written minus 1, and instead of I square, we will write minus 1, and that is minus 1 into minus 1 is equal to 1. So it is clear that AB whole to raise power minus 2 is not equal to B to raise power minus 2, A to raise power minus 2. Okay. And the second part was, what can be given to the name to the property A, B, C inverse is equal to C inverse, B inverse, A inverse. So the appropriate name is socks, shoes, boot, boots property. So that's all about this video. If this video is interesting, then please subscribe the channel and like the video.